Moving on, let's now examine a complete discharge. Let's skip the handholding and see if you can model a complete discharge by yourself with the knowledge that the discharge begins with a capacitor having a starting voltage of 18 volts, positive to negative, top to bottom. Let's assume the discharge process begins at some other t equals 0, at which point the knife switch is toggled to position 2. It is far easier to assume another t equals 0 and simply cut and paste the subsequent discharge onto our previous analysis of the complete charge than it is to incorporate a 32.5 second offset into the discharge equations. If you want a task list, here it is. First, see if you can solve for the time constant associated with the discharge process when the 6,500 microfarad capacitor is discharged through R2, also a 1 kilo ohm resistor. Next, determine the initial values at the start of the discharge process for voltage across the capacitor, current through the capacitor, voltage across R2, and current through R2. Don't worry about the electrical properties for R1 during the discharge process, since the knife switch in position 2 isolates R1. Then, determine the final values at the end of the discharge process for voltage across the capacitor, current through the capacitor, voltage across R2, and current through R2 after a full discharge of 5 time constants. Then, see if you can determine the time-variant expressions for voltage across the capacitor, current through the capacitor, voltage across R2, and current through R2 during the discharge process. Again, to make your job easy, my advice would be to simply assume the discharge starts at another t equals 0. This method sure beats including a 32.5 second offset into each and every equation. Given these time-variant expressions, see if you can determine the instantaneous values for voltage across the capacitor, current through the capacitor, voltage across R2, and current through R2 3 seconds into the discharge process. Finally, see if you can determine the time voltage across the discharging capacitor will have dropped to 5 volts. At this same moment in time, determine the instantaneous values for current through the capacitor, voltage across R2, and current through R2. Now before you go off marching into the blackberries with this task list in hand, I need to remind you that orientation of instrumentation in the circuit remains as illustrated. If current flow reverses direction during the discharge process, hint hint, one might anticipate certain properties to experience negative values. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. Substituting in our given values for R2 in the capacitor, we find the time constant for the discharge process to also be 6.5 seconds. As previously, this should give us plenty of time to watch the process unfold in real time. A complete discharge should take 5 times 6.5 seconds, or 32.5 seconds. The initial voltage across the capacitor at the onset of the discharge is that value we obtained during the previous charge, in this case 18 volts. Given there are only 2 elements in this discharge path, R2 also experiences an initial differential of 18 volts. An application of Ohm's law demonstrates that R2 will experience an initial surge of approximately 18 milliamperes. The discharging capacitor must therefore be supplying 18 milliamperes at the onset of the discharge. Current is coming out of the discharging capacitor rather than into it. To account for this reversal of current, the instantaneous value of current through the capacitor is to be considered negative. These are the start points for the discharge process. If we let the discharge process unfold for a full 5 time constants, or 32.5 seconds, we'd expect voltage across each element to drop to 0 volts and discharge current to cease. These are the endpoints for the discharge process. We have the start points, the endpoints, and the time constant. Current through the capacitor IC of t can be expressed as negative 18 milliamperes times e to the negative t over 6.5 seconds, where 18 milliamperes is the magnitude of the initial discharge current surge, and the negative sign indicates current is leaving the discharging capacitor. Current out of the capacitor will spike to negative 18 milliamperes and drop to 0 by 32.5 seconds. Voltage across the capacitor as a function of time, Vc of t, can be expressed as 18 volts times e to the negative t over 6.5 seconds. Voltage across the discharging capacitor will start at the previously obtained value of 18 volts and drop to 0 volts by 32.5 seconds. Current through R2, IR2 of t, can be expressed as 18 milliamperes times e to the negative t over 6.5 seconds, where the positive sign indicates current is entering R2 and out left to right. Current through R2 will spike to 18 milliamperes and drop to 0 by 32.5 seconds. Finally, voltage across R2 as a function of time, VR2 of t, can also be expressed as 18 volts times e to the negative t over 6.5 seconds. Voltage across R2 will start at 18 volts and drop to 0 volts by 32.5 seconds. Given these time-variant expressions, we can now solve for instantaneous values at specific times and solve for time values that yield specific conditions. 3 seconds into the discharge process, the time-varying expression for voltage across the capacitor demonstrates the capacitor will have discharged to roughly 11.3 volts. An application of Kirchhoff's voltage law demonstrates that R2 also experiences an 11.3 volt drop. An application of Ohm's law demonstrates R2 will experience 11.3 milliamperes of current. This means 3 seconds into the discharge process, the capacitor must be supplying 11.3 milliamperes of current, or negative 11.3 milliamperes, when the negative sign indicates reversal. Current is leaving the discharging capacitor and entering R2. We can also use these time-varying expressions to solve for time values that satisfy specific conditions. We've been tasked to determine the time it takes to discharge the capacitor down to 5 volts. Algebraic manipulation of the voltage across the capacitor as a function of time equation demonstrates the capacitor will discharge down to 5 volts by roughly 8.3 seconds. At this same moment in time, an application of Kirchhoff's voltage law demonstrates that R2 will also experience a 5 volt drop. An application of Ohm's law demonstrates R2 will experience 5 milliamperes of current. This means 8.3 seconds into the discharge process, the capacitor will be supplying 5 milliamperes of current, or negative 5 milliamperes, when the negative sign indicates reversal. There you have it. Not only have we modeled a complete discharge process, we know the instantaneous values of electrical properties at specific times. Let's see if cold hard reality meets these expectations to a reasonable degree of accuracy. I'll let the discharge process run through once with some minimal commentary, and then go through it again, stopping at specific points along the way. The moment the knife switch is moved to position 2 at another t equals 0, we start the discharge process. Current through R2 and out of the capacitor experiences an initial spike, which then starts to subside. Note the negative sign for the capacitor current indicates reversal, i.e. current is coming out of the discharging capacitor. Voltage across the discharging capacitor drops. As current tapers off, voltage across R2 also drops. After 32-ish seconds, voltage across the discharging capacitor and R2 effectively flatlines at roughly 0 volts. Current through the discharge circuit grinds to a halt. This ends the complete discharge process. Looks good so far. Let's see if it passes close inspection. Let's start the discharge process again and pause it along the way for some thrilling play-by-play commentary. The moment the knife switch is moved to position 2 at another t equals 0, we start the discharge process. The fully charged capacitor starts the discharge process at 18 volts, as does R2. Current through R2 and out of the discharging capacitor spikes to roughly 18 milliamperes, where current leaving the capacitor is accounted for by use of a negative sign. The meters display what we anticipated to a reasonable degree of accuracy. 3 seconds into the discharge process, it looks like voltage across the discharging capacitor in R2 is dropped to 11.8 volts and 11.6 volts. This is super close to our anticipated value of 11.3 volts. After the initial spike, current out of the discharging capacitor and through R2 is dropped to respectively negative 12 and 11.8 milliamperes, where current leaving the capacitor is accounted for by use of a negative sign. This is super close to our anticipated value of 11.3 milliamperes. When voltage across the discharging capacitor is dropped to 5 volts, roughly 5.3 seconds later, 8.3 seconds into the discharge process, looks like current through R2 and out of the discharging capacitor is dropped to 5.1 milliamperes, where current leaving the capacitor is accounted for by use of a negative sign. This is super close to our anticipated value of 5 milliamperes. The rest of the discharge process slowly unfolds until voltage across the capacitor in R2 flatlines at 0 volts after a full 32.5 second discharge. At the same time, voltage drops to 0 volts, current through the discharge circuit ceases altogether. This is exactly what we anticipated. If we were to replay and pause the video of the charge and discharge process at regular intervals, and then plot the experimentally obtained instantaneous values, we'd obtain plots that look something like this. During the charging process, current rushes through R2 and into the capacitor. While charging, voltage across the capacitor rises. During the discharge process, current rushes out of the capacitor and through R2. While discharging, voltage across the capacitor drops. Any voltage experienced by any resistor is simply a consequence of the incoming and outgoing current experienced by the capacitor during the charge or discharge process. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or a sudden reversal in polarity. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. In summary, our observations matched our expectations to a reasonable degree of accuracy, and all is well and good in the world. I want you to put your hand on top of the internet and repeat after me. I state your name. Do hereby believe it is within my capacity to model a real-world capacitor charge and discharge process using the circuit analysis skills thus far presented. In summary, imagine how well lab will go if you know what you're doing. Hope you enjoyed this practical demonstration of the capacitor charge and discharge process as much as I did and managed to learn something along the way.